Good evening. I'm Stuart Henderson, Director of Jefferson Lab. It's my privilege to welcome you to our first virtual field trip for families. Jefferson Lab is one of 17 national labs funded by the Department of Energy. It's also the home of a unique research facility, the Continuous Electron Beam Accelerator Facility, a world-leading research tool for enabling explorations of the particles and forces that form the nucleus of the atom and all matter as we know it. Tonight's event will take you deep inside CEBAF, the world's first large-scale superconducting radio frequency of CEBAF's unique research hall. You'll also visit the world's largest cryogenic refrigerators and get a glimpse inside labs dedicated to pushing the frontier through superconducting accelerator technology, research and development. Our expert scientists and engineers are your personal guides, and after presenting each area, they will be on hand to take any questions you may have about Jefferson Lab's research and carry it out. And scientific users, let me say that we're proud of the science that we do, and we're happy that you've joined us to learn more about Virginia's national. Thank you for your time, and we hope you enjoy your visit.
Senior staff scientist to take us to our Continuous Electron Beam Accelerators facility, the main of our research. Welcome to CEBAF.
The Continuous Electron Beam Accelerator Facility, or CEBAF, is the world's most powerful microscope for studying the nucleus of the atom. Experiments in CEBAF are powered by the CEBAF Accelerator, which provides electron beams for research to 4 unique experimental. CEBAF is about 25 feet below ground, built on the Yorktown Formation, an ancient seabed. Electron beams start in the injector, where laser beams electrons from atoms. Then the electrons enter a section of linear accelerator. There they are boosted with energy by superconducting radio frequency energy waves. All along its journey around the accelerator, the electron beam is powerful magnets. With each lap around the accelerator, electrons in the beam gain 2 billion electron volts of energy. An electron can travel around the 7/8 mile accelerator up to 5 times in just 22 millionths of a second before it's directed into a research hall for experiments.
So my name is Todd Sadogata. I am an accelerator physicist here at Jefferson Lab. Here we are in the Machine Control Center for the CEBAF Accelerator. The brain of how operations occur here at CEBAF. Behind me, you can see a group of accelerator physicists and operators tuning up and setting up the accelerator, looking at the screen behind me and all of the small screens behind us. Typically, this room has one main control room crew chief who is in charge of the entire operation in this room, other operators working with that crew chief, and then accelerator physicists like myself advising them to open up the accelerator. After this, we'll go downstairs into the CEBAF accelerator itself, where you'll get to see the real portions and parts of the machine, the technology that makes up our accelerator. So we are downstairs here in the CEBAF accelerator complex itself. Right next to me, this large silver device is what we call a cryo. It stores liquid helium flowing through this from the world's largest helium refrigerator to 2 degrees. Inside these cavities are not just that liquid helium. What are they cooling? They're cooling RF cavities, radio frequency cavities. These are devices that are used to accelerate the electrons through this accelerator. accelerate the electrons, they use electromagnetic with those electromagnetic fields at 1.5 million times per second, 1.5 gigahertz we call it. Those devices are fed through electromagnetic channels that you see here, much like your microwave at home, with power that goes into those electromagnetic bells to accelerate those particles through this complex. Those electrons are accelerated through this linear accelerator, through many of these devices, many times, 5.5 times around the entire accelerator. So while we're running, you actually get 5 different beams of electrons simultaneously, all at different energies, to our experiments and allow us to perform different types of experiments. The energy that they get up to is much higher than even the rest mass energy of the electron. You may have heard of E equals mc squared, Einstein's famous equation. Well, the mass of the electron is really small. Electrons are tiny, but if you put this electromagnetic energy into these electrons and accelerate them, what we find is that they actually get much more energy moving, this kinetic energy, this energy of motion, than they do stored within their E equals mc squared rest mass. Literally about 20,000 times the rest mass of the electron goes into the electrons going through the CEBAF accelerator, around and around, and then eventually out to the experimental stations that you'll visit later. What we're going to do after this is we're going to see where those 5 different beams of electrons come together and combine into the one beam that goes through these RF cavities and gets accelerated through the complex. So we are downstairs in the CEBAF accelerator near the end of one of the arcs. The arcs are the circular portion of the accelerator that bend the beam around to be re-accelerated through the RF cavities. Here you see actually several different arcs, several different beam pipe. These are different energies of electrons. The electrons in the top have only gone through the RF systems and been accelerated once, while the electrons on them have been accelerated through those RF cavities 5 different times and have almost 5 times as much energy. These various energies of electrons then come back together, much like light enter a prism and get recombined into white light. Those electrons come back together and go back through the linear accelerator again, which accelerates all those different energies of electrons simultaneously. So you can see different objects here. I pointed out the silvery vacuum pipes because the electrons have to go through quite a low vacuum, a vacuum that is close to interplanetary space. You also see behind us magnets. These magnets are used to focus and bend the electrons around our. These smaller magnets that are right here behind me are called quadrupoles. They have 4 poles, 2 north and 2 south poles, and they form a magnetic field that keeps the electrons together and keeps them from spreading out too widely like a flashlight beam in the sky. And they keep our electrons confined as they go around our accelerator. But our electrons not only have to stay focused, they have to change direction as well. So behind us, those big blue magnets are dipole magnets. One north, poles, a dipole. Dipole magnets simply bend the electrons around the accelerator. If we assemble enough of these dipole magnets, we can bend the electrons around 180 degrees and have them come back to the entrance of one of those linear accelerators made up of RF cavities and get re-accelerated through the complex. So there are 2 fundamental parts to a particle accelerator. The RF cavities that you've seen produce the electric fields that accelerate the electrons up to higher energy. Those are in the cryo modules, cooled down to 2 degrees above absolute zero. However, you have to take those electrons and also keep them together and not let them spread out and steer them to where you want them to go. That's the job of the magnets behind us. Quadrupoles focus the beams, much like a lens would focus light, and the dipole prism would bend light. The dipoles behind us bend the electrons around the accelerator so they can go around a loop and return RF to be accelerated again and again. Throughout the entire accelerator, the electrons are accelerated 5 times through each linear accelerator portion of the accelerator, 5 and actually a 6th time through one portion as well, before they go out to the experimental halls where they hit targets and image the nuclei of atoms to be used in nuclear physics experiments. This is your tour of the CEBAF Accelerator. Thank you for joining us for this tour of CEBAF.
Wow, what great information, Todd. And I apologize to everyone on the YouTube Live. We are experiencing some technical issues. We're working it out now, but I hope that you will stick with us as we get through these glitches, and we'll have a great experience for you. We are joined now by Todd Live to answer some of your questions about CEBAF. We have about 5 minutes for each speaker, so we will get to as many of these questions as we can in the allotted time. We'll start with this question, Todd. What type of information does the big screen in the control room show?
Sure, that big screen actually has a ton of information. That's why it's the big screen that dominates the room. It shows us the status of all of the RF cavities in the accelerator. Many, over 100 of them. It shows us the beam intensity going to all of the different experiments and all of the different, whether the beam is on, whether the beam is off, where the beam is going in certain specific locations around the accelerator. A ton of information that we take in just with a glance of looking at that huge screen, and it's incredibly useful in running this big particle accelerator.
That's great, thank you. So how far underground is the accelerator?
The CEBAF tunnel itself, where the accelerator is about 25 or 30 feet underground. You can think of it as a couple of stories. It's not nearly as far underground as some big accelerators, like the Large Hadron Collider at CERN that you may have. 25 to 30 feet underground. Takes a few stairs to walk downstairs when we want to work on the particle accelerator, when we want to work on CEBAF.
Okay, what advice would you give to a student physicist?
For students who want to become physicists, my gosh, I'd say there are two really good pieces of advice from my own experience. The first, get your hands on. I became obsessed with science by reading magazines, by reading books, by reading good science writing. And there are a ton of really good science writers working in the field nowadays. So read. Even with videos on YouTube, reading really gives you in-depth information that you can't get otherwise. The other thing I would suggest is find a good mentor, whether somebody at your school or somebody that your parents might know who can mentor you and maybe even open some doors and give you opportunities in the field. Because when you start engaging that way personally in a relationship, you'll find that a lot of opportunities open up.
That's great advice, Todd. Thank you. How long does it take an electron to travel all the way through CEBAF? So
the CEBAF, that big accelerator, is about 7/8 of a mile around. It's about 1.3 kilometers if you work in kilometers, but 7/8 of a mile around. And the electrons go around the entire accelerator 5.5 times. Now you might think, that's almost 5 miles of track that these things are going through, but they're also traveling very, very close to the speed of light. And they traverse that almost 5 miles of particle accelerator, not in a second, not in a thousandth of a second, in 25 millionths of a second. We call it 25 microseconds is how long it takes an electron to go from the start to the end to the experiments.
That's great. And we have one chance for one more question. How many magnets are in the accelerator?
Gosh, that is a good question. I have not walked through the accelerator and counted them myself. In each of those big arcs, we have about 30 of those bending magnets, the dipole magnets that I talked about. And there are 10 of those arcs, so there are about 300 of bending magnets. We have, let's say, about 500 or 600 in the accelerator. Those bends are dominated by magnets, and then those long straight sections are dominated by those RF cavities that give the particles the energy they need to get out to the experiments that you'll see next.
Thank you so much, Todd. Next up is our newest experimental hall. Let's join Mark, staff scientist with Hall D, on a tour of their latest experiment.
Hall D is the newest of Jefferson Lab experimental halls and was built as part of the CEBAF 12 GeV upgrade project, completed in 2017. Located on the opposite corner of the CEBAF accelerator from the other three halls, Hall D is the only one that receives the highest electrons generated in CEBAF. On entering the Hall D complex, the electrons strike a razor-thin slice of diamond, generating a beam of high-energy photons used in experiments. Scientists hope to capture hybrid mesons in Hall D. These particles are made up of the same building blocks as protons and neutrons, called quarks, but also contain an active component of the strong force, or glue, that binds the quarks tightly together. Hall D experimental data will help scientists from around the world reveal new subatomic particles, help solve the mystery of why quarks are never found alone, and shed light on the mysterious strong force that binds together every nucleus in every atom in the universe.
Welcome to Hall D! My name is Mark Dalton, and we're here in Hall D, where I am a staff scientist. Behind me, you see the apparatus that we use for our experiments. We are interested in studying the strong nuclear force, which is the force that binds neutrons and protons together to form nuclei, and it's the same force that binds quarks together to form the neutrons and the protons. Now, quarks are fundamental elementary particles that feel the strong force. The way we study strong force here in Hall D is through spectroscopy. So spectroscopy is the act of trying to map out all of the possibilities that can be found in nature. And in particular, we are interested in a family of hypothetical particles called hybrid mesons. If we produce a hybrid meson in our apparatus, then it will decay almost instantaneously into a large number of daughter particles, maybe 5, 10. So the Hall D has been designed specifically to detect many particles at the same time. In addition, we've been pushing the technological envelope to be able to take data at really high rates. And by doing that, study very races. So producing a hybrid meson is expected to be. Now, a scattering experiment like we have here requires 3 important ingredients. It requires a beam, it requires a target, and it requires detectors to detect what is produced in the interaction. So why don't we go now and have a look at where our beam is produced. This is the Tagger Hall where we produce our high energy photons. We take the highest energy electrons from the accelerator and pass them through a piece of diamond. We align the diamond precisely with the electron beam to produce photons with a specific energy and polarization. We then tag the photons, which is why this is called the Tagger Hall, by detecting the electrons that we used to create those photons. And that is done with this large magnet that you see to my right. Once we have produced the photons, they travel 75 meters or 250 feet downstream to the experiment. Why don't we go and have the photons go now? We're here in the Collimator Cave, where the photon beam travels through a small 5-millimeter hole that we call the collimator. The purpose of the collimator is to remove some of the low energy unpolarized beam so that what remains is higher energy and more polarized, which is what we want for our experiment. Following the hole, we have some permanent dipole magnets which remove any charged particles from the beam so that they can our experiment. And we're going to have a look at the experiment now. Here we have the next ingredient that we need. That's our target. Our target is a 30 centimeter long of liquid hydrogen. And we use hydrogen composed of a proton and an electron. And we want to scatter our photon because it's the simplest nuclear system. And that makes it easier for us to understand the products that are produced in the scattering so that we can find our hybrid mesons. When we use the target, it's going to be pushed forward into the apparatus. So what you see behind me is our superconducting solenoid magnet. That is the red cylinder. It's kind of like a big MRI magnet, but bigger, so that an adult can almost stand up inside it. Within the magnet, we have a whole bunch of detectors that we use to detect what comes out of it. We have tracking detectors to detect our charged particles. We have calorimeters to detect our neutral particles. And then we have scintillators to detect the time when they travel through it. Target, we have scintillators which measure the start time when the interaction first occurs. In front of the magnet, we have some more detectors which are there to detect particles that go in the far forward direction. So why don't we go have a look at those detectors now. I'm standing here on our forward carriage, which is the most forward part of the experiment. Behind me, you see the forward calorimeter, and these are the last detectors that the particles will interact with. They're designed specifically for neutral particles. You can't see the detectors themselves because of all the cabling that's required to take the signals from the detectors to our electronics. The beam itself comes through that square hole that you see behind me. Once the signals are produced in the detectors, they travel on these cables to our electronics over here. We have more than 30,000 different detector elements in our experiment, and each one has to be individually read out. So we have a lot of electronics to do that. What you see here are some that are bringing the signals to the electronics, where the signals are partially analyzed and connected together. All of the electronics you see system designed at Jefferson Lab. Once the have been digitized, they are sent upstairs to our counting house for further analysis. We're going to have a look at the counting house where that is done. This is the whole where physicists control and monitor the experiment that's going on down in. When the experiment is running, there are 2 physicists here at all times, and everything is working correctly. But there is space for more people to work here when things get interesting. The signals from the experiment come upstairs and into our electronics room, which you see behind me, where they're combined and analyzed. We fully analyze a fraction of the events to make sure that things are working correctly, and all the events are saved in long-term storage so that we can later analyze them using high-performance computing. Hall D is the newest hall at Jefferson Lab. We have a photon beam and a proton target, and we're looking for hybrid mesons. I'm Mark Dalton for visiting us here in Hall D.
So many amazing things to see in Hall D. We now have Mark here for our live Q&A. Mark, thank you for joining us today. Let's start with this question. There was one in the live that they asked, it appears that there are 3 experimental shells. How many experiments simultaneously?
Well, we actually have 4 experimental halls, and it's possible to run experiments in all 4 at the same time. And the accelerator does a very good job of use radio frequency magnets to switch the beam from hall to hall. So each hall can get a little piece of beam every 4 nanoseconds, and that's what we get in hall D. And then 4 nanoseconds later, another hall will get a little piece of beam. So we share.
Okay, great. Why do you tag the photons that you produce, and what does that tell you?
So when you do a physics experiment with a beam, you really need to know the energy of the particle that's coming in. The CEBAF accelerator produces electrons of a very well-known energy. But when we create our photons, they come out with a range of energies. We use the conservation of energy to figure out what the energy of the photon was, because we can detect the electron. And by using the known energy of the detected electron, we infer what the energy of our photon in the photon beam was.
Okay, great. This is a question about how did you become a physicist?
Well, I've always had an interest in sort of understanding how the world works. As a child, I was very curious, and mathematics and science. So I feel like it was a path that I was quite likely to end up on, but I have a family member who's a physicist, and so he really encouraged me and was always telling me a lot of fascinating stories about the work that he was doing, and acted as a mentor for me, and that really helped me to engage in physics as a career.
Okay, so why is your target shaped the way in Hall D?
So our target is, it's long, 30 centimeters long and thin, and that's basically because the beam is long and thin. So we build a detector that can handle a certain amount of scattering rate, and we want to maximize as much rate as we can so that we get as much data as we can. And the amount of scattering depends on how much beam you have and how much target you have. And by making a thicker or longer target, you are able to decrease the amount of beam that you have to use for the same scattering rate. And by decreasing the amount of beam that we use, the amount of photons that we use also decreases the amount of electrons that we need, and that decreases the amount of electrons that are in our tagger. And so it decreases the backgrounds that we see in our tagger. So it's a little experimental technique that we use to reduce backgrounds.
Okay, great. And this is the last question we have time for today. What types of particles do you make and detect in your experiments?
So whenever you have a high energy beam and you put it into a target system, you'll make just a huge number of particles. You basically make every possible particle mass lighter than the energy that you're putting into the system. And so we're making the hybrid mesons, presumably, that we're looking for. And then we're also making a whole bunch of conventional mesons, and we're also making baryons. So that gives us a lot of opportunities actually to look for and study various different particles, although we're focused on the hybrid mesons. But we've, for example, detected the J-psi meson and done some very interesting work on that. But by far the most common particle that we produce is pions, because they are the lightest meson.
Okay, that's all the time we have for this segment, Mark. Thank you so much. Now we will move on to Hall B with Latifa, a senior staff scientist who is going to take us to CLAS, which in this case means our CEBAF Large Acceptance Spectrometer.
Hall B is the smallest of Jefferson Lab's 4 experimental halls. It is equipped with the 12 GeV Large Acceptance Spectrometer, or CLAS 12 for short. CLAS 12 is a large system of detectors for tracking and measuring subatomic particles. As experiments begin, it is inserted into a recessed niche in the CLAS 12 detector systems, so that the detectors almost completely surround the target. Electron beams enter the target and interact with the particles inside, such as nuclei, the protons and neutrons in the nucleus, or their quarks. Collisions inside the target are measured in the CLAS 12 detectors, which can record several terabytes of experimental data. Experiments carried out at Hall B are fundamental investigations into the nature of matter, aimed at focusing and shaping our understanding of nuclear physics from the subatomic scale to the
Welcome to Hall B. This is one of the 4 experimental halls at Jefferson Lab. It is the smallest hall, but the one with the large acceptance spectrometer. My name is Latifa El Wadghiri. I'm a nuclear physicist here in the lab, and I will guide you to the tour of Hall B. But before I do that and explain to you how the experiment works, I would like to explain to you our scientific mission. What we are after is to understand how the protons and neutrons, which are the basic building blocks of the nucleon, together by the strong force. So the distribution of this force must be in such a way that prevent the proton from decaying, which allow us and all the visible matter in the universe to exist. So as part of the upgrade, what was here before was a detector called CLAS, which stands for CEBAF, Large Acceptance. It operated from 1997 to 2012. Then it has been replaced by state-of-the-art detector as the Class 12, keeping CLAS in the name as Large Acceptance Spectrometer. Has been optimized to operate at 12 GeV. Now I will describe to you the detector, how Class 12 detector looks like in the model. Then I will walk you through the. So the beam of electrons is coming in this direction, and the Class 12 is divided in 2 parts. The central detector here, at its core, is superconducting solenoid magnets, and the forward detector is at its core a toroidal magnet. Both forward detector and central detector are equipped with detection system to identify completely the produced during the interaction. So the electron can interact with the target. There is scattered electron that we use in the forward direction in coincidence with all the particles in the final state. So now we will look at the details of the forward detector, and at our last stop we will look at the detail of the central detector. So what you see here is what we call the detector. After the interaction of the beam with the target, all the forward-going particles are detected here. Downstream of the target is the Cherenkov counter that is designed to separate electrons from other charged particles. And since it's a detector that's for the tracking system, it has to be as light as possible. So special attention had to be done in the construction of the mirror. It is followed by what drift chambers to measure the angular scattering angle and the moment of particles. There are 3 of them: region 1, region 2, and the region 3. Region 1 sits before the torus magnets, region 2 inside the coil magnet, and the region 3 outside. So the combination of these 3 regions give us scattering angle and the momentum of the particle. Then now the charged particle, if they are negative or positive, and now we need to determine their particle ID. This is achieved, but what you see here, the time of light, measure the timing of the particle with precision to 120 picosecond. It's followed by the colorimeter that measures the neutral particles, photons and neutrons, and also illumination of the electron. In between the time of light and the last region of the drift chambers, there are other detectors. These are low threshold Cherenkov for pion identification, and one sector for the first experiment was equipped with a ring imaging to separate different charged particles. And that is really the forward detector. Next, we will see the central detector. So what you see here is the central detector of the Class 12. High energy beam, very precise, come this direction, interact with the target that will be sitting at the center of the core of the central detector, which is the superconducting solenoid. The superconducting solenoid is 5 Tesla. It is designed for magnetic analysis for low momentum, and also it is designed to shield the detector to operate at higher rate, shielding it from the electromagnetic background. These are the tracking system that you see here in the retracted position. composed of silicon detector and by time-of-flight system for charged particle identification and for neutral particle identification. So that's complete the description of class 12 detector centered forward. The success of the construction of class 12, its commissioning, and now its operation and data analysis and extraction of physics was only possible in the best team from international collaboration, team of physicists, engineers, technicians, and students. So thank you for stopping by and checking our state-of-the-art detector. Thank you.
Latifa, thank you for that exciting tour. I have several questions for you, and we will keep going as the time allows. The first one is, you mentioned the universe at the beginning. What is the relation between the research you do and the understanding of the universe?
Well, thank you so much for this great question. So our goal is really to understand the fundamental structure of all the visible matter in the universe. And in Hall B, we do that in many ways. For example, studying the 3D imaging of the nucleon, where we detect all the particles that are produced in the final state and have what we call the nucleon tomography that enable us to get insight to the internal forces and the strong force. The other way is we want also to understand the transition between the phase where we have free quark and gluon, non-interactive, to really forming the stable proton and neutron that form all the visible matter. And we do that by studying what we call the excited state of the nucleon that occur just 1 microsecond after the Big Bang, and they play an important role in this transition. Although we cannot really recreate the original environment of the universe, we study with a very high precision this event in high precision in isolation.
Okay, great. Can you tell us what makes class 12 unique in comparison to the other experiments at Jefferson Lab and worldwide?
Well, class 12, as it indicates, is CEBAF large acceptance spectrometer, and 12 operates at 12 GeV. It was an upgrade of the existing class, CEBAF large acceptance spectrometer. It has the capability to detect, as large acceptance, to detect many particles in final state in coincidence. And this is important in particular to do the 3D imaging of the nucleon and nucleon tomography, because it's important to understand and have all the information about all the kinematical dependence of the particles. So that's one thing, but also operating large acceptance spectrometer at high rate. The processes that we're looking at are processes that are very rare. So, and we to increase the rate of the data acquisition. So it's the only acceptance in the world that operates at fixed target, high luminosity. So it's large acceptance, high luminosity, and also flexible trigger to allow also for potential discovery.
Okay, great. The next question we have from the Q&A is, what do the particles have to be sped up? Why do the particles have to be sped up?
Well, you come with a very high energy electron, and in our case, we have station targets inside the detector, and with the Einstein equation, E = mc squared. So you come with high energy electron, targets at rest, and you have to produce particles in the final state. So, and we count for all the particles in the final state for conservation, using conservation of energy and momentum. And of course, the detectors are the messenger of the fundamental interactions that happen at the center.
Okay, great. So how did you become a physicist?
That's a very, very nice story, actually. It's when I was in high school, I took my first course in physics, and it's important to listen to your teachers. And I had a great teacher. Then that summer, I was so curious about how the world works and physics, and I bought my first physics book from the flea market. And it happened to be a book by Heisenberg, the Nobel Prize winner, 1932, talking about duality between wave and particles. And I was fascinated by that. And it happened that I am doing this science today. And just to tell you, I was born in Morocco, where the United States was very, very far dream. So I'm really excited to be able to do this research. And it's really all about the passion. It's being passionate about this topic you want to study. And give it all what you have.
Thank you, Latifa. And wrapping up with our last question, how do students contribute to the research you do in Hall B?
Students contribute tremendously to the research we do in Hall B at all phases. From really doing small projects, prototyping, hands-on, computing simulation, data analysis, and also at data taking and data analysis, and also at high-level analysis, working with peers. So, and we have students that worked with us from high school students to undergraduate students to graduate students, and of course, postdocs. So, students made tremendous contribution to the Class 12 construction and data analysis.
Thank you so much, Latifa. Our next hall tour brings us to Brad, a staff scientist in Hall C, our largest experimental hall.
Welcome to Experimental Hall C, Jefferson Lab. Hall C is 20 feet in diameter and 60 feet tall. The first experimental hall to begin taking data at Jefferson Lab in 1995. During experiments conducted in Hall C, electron beams from CEBAF enter the hall through an elevated pipe and are directed into an experimental target. A target might be any gas, liquid, or solid, which can also be polarized or cryogenically cooled. Inside the target, with individual nuclei and the subatomic particles inside them. Two high-momentum spectrometers, or detector systems, capture and measure the particles that emerge from these collisions. Experiments conducted in Hall C typically focus on studies of the properties of the subatomic particles that build our visible universe, including atomic nuclei, protons, neutrons, and quarks.
Hall C. My name is I'm a physicist and a staff. The bulk of my research, along with a huge team of other physicists, engineers, and technicians, in this experimental hall and in its sister hall, Experimental Hall A. Now, this hall is the largest experimental hall on the JPL, and one of the reasons for that is so that it can accommodate this huge detector device here. The scale of it is a little hard to tell between you and I on camera here on this tour. I'm going to walk backwards and you can get a better feel for just how big this system is. One of these detector packages weighs on 1.5 million pounds, about 2 train locomotives stacked on top of each other, and the whole thing can pivot about our target, what we're trying to, which is off to my left, and we'll talk about that a little more in the future. This whole system on this green carriage behind me can rotate about that target center, and we'll see some rails and the big wheels that drive that motion in the future. So the next thing that we're going to do is an experiment that we do in this hall, and we're going to start where the beam into the experimental hall, the beamline. Welcome to the beamline. This is where the electron beam comes from the accelerator, coming from headed this direction towards the target, which is behind me. It travels inside this silver pipe that you can see off to this side. The electrons come from the accelerator with so much energy pushed into them that they weigh 22,000 times more than they used to when they started out over in the injector at the beginning of their journey into the hall. The reason for that is the famous Einstein's equation, E equals mc squared. So can't get that electron moving faster than the speed of light, so all the energy that the accelerator particle goes into its mass. Those particles come down here, and because they're so heavy inside the target, probe the kinds of things that we want to study here at Jefferson Lab. Now, in a typical experiment here, the experimentalist, myself, and our team would ask Accelerator for beam with certain properties, set their accelerator up and deliver it to the hall, but we don't trust them. So we're good experimentalists, we have to measure everything. You see a whole bunch of devices along this beamline that are used to control characteristics of that electron. We measure along this line upstream before this beam hits the target characteristics like how many electrons are coming in per second, that's the beam current. Its position, we can measure within a fraction of a millimeter, so something on the scale of the thickness of a human hair. And that electron beam itself is already constrained so that it's like this thin thread of electrons traveling right down the middle of this silver pipe. Inside there is hard vacuum because we don't want that electron beam striking anything. And that cross-section, the area of that electron beam is again on the scale of a human hair. All the way from the injector down to the target. And we need to know that, just exactly where we're hitting our target. One of the unique things about Jefferson Lab is how well we can control the spin of the electron. Spin is a property of most fundamental particles where they behave like they're balls spinning on an axis. And that rotation axis we can align in whatever direction we want. And those electrons come in and strike our target, different things will happen depending on the direction of that spin. So being able to control that spin direction when it comes in to strike our proton, our neutron, our nucleus, or individual quarks inside the proton and neutron, that gives us an extra handle to better understand proton and neutron, or the quarks or anything else that we're trying to study. The next step, I'm going to take you on the other side of the target, where we can see the target. The beam's still going to be coming towards me, but we'll be able to see the target and the two detector packages, the SHMS and the HMS spectrometers, to the right and left of me. All right, here we are on the other side of the target. If you look straight above me, there's quite a large diameter. We place our targets inside that cylinder, and then we pump all the air out, because again, we interact with the target, the proton target, the neutron target, the nuclear target that we're interested in studying. So that's right above me. And off on my left, you can see this expanding tube that the rear of the hall, which is that direction. We refer to that as the exit. So one of the frustrating things as an experimentalist is that we go to all this effort, I'm sure for the accelerator scientists as well, we go to all this effort to get this finely tuned electron beam that I was discussing earlier. But on the electrons, everything around us, the solid material that I'm made of, is most vacuum. So 99.9% of those electrons will pass right through that target, and they go all the way down into what we refer to as the beam dump. This facility can deliver a megawatt of beam power, all tightly constrained in these precisely oriented electrons, and we're only able to use, and it's fascinating when you think about it, because we use a whole slew of different types of targets. Liquid targets, often liquid hydrogen, liquid helium, carbon targets, basically graphite. It's the same stuff that's in your pencil. It's that hard, you can't see through it, and yet 99.9% of the electrons that we send at that target will pass right through and they won't see a thing. Most of the space on the scales that we're probing has got nothing in it. It's vacuum. The basic experiment that we do in this hall is we've got the electrons that I discussed coming in straight at the target that we've ordered up with certain characteristics, certain energy, the spin is pointing in a certain direction. We know exactly how it's coming in and hitting the target. We've got that electron coming in, it strikes the target, and then we set one of these spectrometer devices up to measure the electron after it is scattered, after it's bounced off the thing we're trying to study. A proton, a neutron, a nucleus, a quark. That electron comes in, it bounces off, one of our devices measures the properties of that electron after it's struck. Exactly what those properties were when they came in. We measure exactly what all of those same properties were after it's bounced, and we take the difference. That tells us exactly how we have struck, how much energy, what direction, what the spin direction was with our target. And the question we ask our theorist friends, what should happen based on what we think is going on, what's holding the particles together inside that target, that proton, that neutron, whatever it is, what will happen if we hit it in just that way? And then we set up our other detector to measure what comes out, and we determine, did that happen or not? If it did happen, great. Our mental picture, our theory of what's inside that target is true. We've got greater confidence that it's accurate. If it's something different, then these two spectrometers on my right and left is they roll on the rails that you can see that I'm stepping over. That allows us to set our system up to measure various circumstances. So we've got that electron coming in, for example. If it comes in and just grazes the target and comes off at a very shallow angle, then it hasn't a lot of energy, more or less, into that target. It comes in and bounces off at 90 degrees, well, then we've dumped a whole lot of energy into the target, and we're agitating, we're target apart in different ways. So these two spectrometers can be moved to different angles in order to help control the variables that we are subjecting that target to. A couple of other things I want to point out. The reason we call these devices spectrometers, off on my right, you can see a big blue hunk of steel. That's called a dipole magnet. It's like a fridge magnet. It's got a north and south pole. That is the workhorse of this device, and there's a similar one over on the SHMS on the other side. The particles will come in and they will bend inside the magnetic field we set up inside that dipole. The heavy stuff will bend less, because it's got a higher momentum. The light stuff will bend more. So we can set up the field inside that magnet to only bend particles with a certain momentum into our detector stack, which is up inside these shield huts. That is where we're going. Welcome to the SHMS detector stack, or detector hut. It's a very heavily shielded container. The dipole that I was discussing just recently, the SHMS spectrometer, is just over here. Particles come from the target, they get bent up. They come through this stack of detectors that we call a detector stack, and we can identify what kind of particle it is, where it is coming through the stack, how much energy it has, and all the other characteristics of the particle that we're interested in. We have devices called Cherenkov detectors here, back behind me. Those help us figure out whether that particle is in a right here, we have what are called tracking detectors, wire chambers in this case, kind of like the bug screen in your window. There are grids of wires that are with wires horizontally, wires vertically. When a particle passes by them, I get a signal from this guy, a signal from this guy. I know where they intersect in space. The X, Y point. I've got one set here, so I can connect the dots. That gives me an idea of exactly where that particle is going. The precision on those measurements is the human hair. Lastly, back behind me, I've got a number of calories in food. It measures the total kinetic energy of the particle. The particle will stop in the final detector back there. And that's where the story ends. So the electron comes in, strikes our target. We measure the electron that hits our target. We see what comes into the other spectrometer. What we think should happen, great. Thanks for coming on this tour of Hall. I hope to see you at a future open house.
What an exciting place to work, Brad. Thank you for walking us through Hall C. I now want to take about 5 minutes to go through some questions from our viewers. On the first question, how do you control the spin of a neutron?
The spin of a neutron. That's actually pretty tricky. The way we do it is there's no free neutron target, so we have to take advantage of nuclei with special properties. And in our Hall, we use helium-3. One of the cool things about helium-3 is that it's got two protons and one neutron, and we can polarize that nucleus, so that combination of the two protons and the neutron, in a particular direction using magnetic fields and lasers and a few other techniques. The because the two protons are in there, they tend to line up with their spins anti-aligned. One's going in one direction, one's going in the other direction. So the interaction of the electrons or the photons, whatever it is we're trying to use to probe what's going on inside that nucleus or the nucleons inside that polarized helium-3, if we can polarize that entire nucleus, then it is the same as, or roughly the same as, polarizing that neutron. So the interactions with the proton tend to cancel out for the things that we're trying to measure, which allows us to really focus in on just the polarized neutron. And that polarized neutron is pointing in the direction that we're able to polarize that entire helium-3 nucleus. There are a few other ways to do it with very, very strong magnetic fields that allow us to sanity check and cross-check the measurements that we make on the polarized helium-3. But that's what we've been using recently.
Great, thanks, Brad. What do you do with the unused beam in the dump?
Oh, yeah. So that's kind of an interesting thing. We go through, I think I mentioned in the video, all this effort, and Accelerator goes through all this effort to get those electrons all with exactly the same energy lined up and moving in exactly the same direction. We take the spin of the electron and the accelerator can point it in whatever direction we, the experimentalists, would like it to point in. And then, ridiculously small fraction of that total electron energy, the electrons going down that beamline, actually interact with a target and are useful to us. So all the rest goes down. We don't want to see what happens to it because it hasn't hit our target, so we're not interested. We don't want it to blur our measurement. So it goes down into what we call the beam dump region, which is a hole at the back of the accelerator, or back at the experimental hall, into what is essentially a giant tub of water. And when it goes through that tub of water, it interacts with all the water molecules and energy gets converted to heat that we then pump away. So we can take a megawatt of beam in the hall and maybe a few tenths of a % of that actually interact and are useful for the experiment. And 99.9% of that beam energy just goes up to heating up a big tub of water at the end of the day. And it's all buried underground, so none of the radiation can get out, and all the energy goes into just heat, which is easy to dispose of.
Great, thank you. So another, you mentioned a sister hall. Which one is that, and how is it different from Hall C?
Yeah, so a sister hall is Hall A. So we're in Hall C, and there's halls A, B, C, and D. Hall A is very much like Hall C. It has two large detector apparatuses called spectrometers in its natural configuration. And those spectrometers are free to move about the hall. They're able to rotate or pivot about the target direction in very much in the same way that the two spectrometers in Hall C are able to do, like I discussed in the video. What we can also do now in Hall A is the older spectrometers, actually what we're doing right now in Hall A is the older spectrometers have been moved, they've been rotated out of the way, and two new customized devices are put into the experimental hall. Those devices can also move around so that we can measure or fine-tune our detector apparatus to really measure exactly what we want when we hit our target, our protons or our neutrons, with the electron beam. So we're calling it, or it's basically turning into what we refer to as a large installation hall, where we can really customize the detector equipment to do things that standard equipment, like the spectrometers in Hall C, the SHMS and HMS, and Class 12 Hall B, and the GluX spectrometer in Hall Delta, aren't really capable of doing. They just do other things. It's all very complementary.
Okay, great. And the last question we have time for, Brad, what types of targets do you use for experiments?
Oh, so a whole variety of targets. One of the targets that we use really all the time, because it's very standard, so we can use it to sanity check that we understand our detector calibrations, things like that, are carbon foils. They're just thin sheets of black carbon, same material that you have inside your mechanical. We also use things like aluminum or gold. We've used tungsten, very, very heavy metal. Like I mentioned, we use gaseous targets like helium. cryogenic targets, hydrogen, deuterium, other materials that we cool down so much that they convert from a gas into a liquid. It really depends what we're trying to measure.
Okay, thank you so much, Brad. Now that you have visited our main accelerator and several of our experiments, it's time to bring you to our research and development operation with Anne-Marie, an SRF R&D physicist with the SRF Institute.
Jefferson Lab is a world leader in superconducting radio frequency, or SRF, accelerator technology and capabilities. In fact, Jefferson Lab was the first facility to successfully implement a large-scale application of SRF accelerating technology in the Continuous Electron Beam Accelerator Facility, or CEBAF. Particle accelerators built with SRF deliver a continuous beam of particles with improved beam quality and lower energy. SRF acceleration capability begins with a called niobium. When cooled to temperatures near absolute zero, can be transmitted through niobium with very little loss to resistance or heat. A string of 8 hollow niobium components, called accelerator cavities, housed in a 6-ton, 30-foot-long individual section of particle accelerator called a cryomodule. Nearly 12,000 individual each cryomodule, which insulates the cavities, allowing them to remain cold and superconducting. Jefferson Lab's SRF Institute pioneers SRF research and development. Build and test one-of-a-kind components, and also assemble, refurbish, and test particle accelerators for research worldwide.
Welcome to the SRF Institute. My name is Anne-Marie Valente Feliciano. I'm a researcher here at Jefferson Lab. The SRF Institute is constituted of scientists, engineers, technicians. We also host postdoctoral scientists and PhD students. At the SRF Institute, we design, prototype, and assemble the basic units of an accelerator, which are called SRF cavities, and we assemble them in cryo units called the cryomodules. Superconducting RF technology aims at accelerating particles, accelerators such as electrons, protons, and the superconducting RF technology is based on the use of superconducting materials such as niobium. The particularity of these materials is that at transition temperature, their electrical resistance becomes very small, almost null. The RF response of these accelerating structures is extremely sensitive to the inner top surface of the structure. So this means that the processing of such structures is extremely critical. The material that we use as sheet material, such as this one, then needs to be shaped and welded together to form a structure such as the one that's behind me. Once the structure is completed, we have to remove every defect and particles that could be residing on the surface. For this, we do process the cavity with mechanical polishing and chemical etching. Because we need to take care to have no particulates on the surface, these processes are taking place into a clean room, such as the one behind me. Near-term research projects, we aim at improving the quality of bulk niobium and its response to RF. For this, we are injecting a little quantity of nitrogen into the surface in a furnace, or we are playing with the natural oxide layer of the material in order to increase its efficiency and its response to the radio frequency. And long-term research projects, we aim at developing surfaces that are based on niobium thin layer on a copper substrate, or by developing alternative materials such as niobium-3 tin or niobium titanium nitride in multi-layer to have transition temperature that is much higher than. Now we're going to leave the cleanroom area and go to our electron beam welding facility, where cavity parts or pieces are stitched together in an electron beam welder to form a complete RF cavity structure. We are now in our electron beam welding facility. Once the niobium material is machined and deep drawn into half cell, different parts of the cavities are welded together in the vacuum chamber that is behind me, where an electron beam is going to fuse the material, melt the material together to at different places in the at the cavity. Here at the iris, where the electrical fields are the highest, once excited radio frequency, or also at the equator, where the magnetic field is the highest. Once we have the cavity that is completed, such as the one that is next to me, the cavity proceeds to chemistry in order to have all defects of the materials. Then it will go into the clean room, where it's going to be cleanly assembled into two. So where the cavity is going to be tested in our vertical test facility in order to see if it meets the specification and it has the efficiency that we're looking for, or it's going to be it will be put together with cavities as a cavity string that will be inserted in the cryo module. This cryo module will be tested in our cryo module testing in order to assess its performance down to the accelerator. Now we're going to proceed to our research and development labs, where we are developing alternative technologies for superconducting RF surfaces, such as the deposition of niobium on copper substrates, and development of superconductors such as niobium-310 and multi-layers based on niobium titanium nitride. Superconducting technology is a multidisciplinary field that encompasses different aspects. Designed to develop innovative schemes of RF acceleration that includes simulations and calculations, the processing of surfaces on the base material, which is bulk niobium, or to create innovative surfaces of copper and multi-layers based on niobium titanium nitride or niobium-310 in the base material bulk niobium to be able to sustain much higher field than it can on its own. Here we have a twin-axis niobium that has been coated on the inside with niobium in our thin diffusion furnace, and here we do have on copper cavity that has been deposited with high power impulse magnetron sputtering with the system that's behind me. I hope that I helped you to get a feel of the activities that we have here at the SRF Institute, and I thank you for joining me today.
We now have Anne-Marie here for our Anne-Marie, thank you for joining us today. In the interest of time, let's just jump right into some questions about your amazing research. What can particle accelerators be used for beyond fundamental science?
All right, actually they can be used in a wide range of needs for both society and industry. For example, they can be used in medicine, for cancer treatments, medical isotopes, production, sterilization of medical instruments. They can be used in wastewater treatment, food sterilization, preservation, modification of material properties, for chemistry. They can also be national security for scanning of incoming cargo, and accelerator systems plants can be operated in a more safe and efficient way. And this is actually, these applications are actually the motivation behind some of our researches at making accelerator more efficient, more powerful, in a smaller footprint and cheaper.
Wonderful. So what was your field of study to become an SRF physicist?
Well, I studied condensed matter physics. I became fascinated in physics, by physics, in high school, and that fascination continued when I got the opportunity to have some internships in research labs at university during my curriculum in university in France. And actually, I was exposed to superconducting in film technology during a fellowship at CERN. And for those that are interested in the field of SRF, I would encourage them to seek mentorship or internship in one of the many DOE lab programs that are available, as well as in some universities that are at every level from high school all the way and going through undergraduate and graduate programs.
Thank you, Anne-Marie. Why do the accelerator cavity structures have different shapes?
So the cavities are different shape because they are a core element of the superconducting accelerator, as they are used to increase the particle velocity of beam. So in the actually in the case of linear accelerator, they're actually the dominant component of the machine. Since there are different types of accelerator, the RF cavities have been optimized with different properties and for different purposes, depending on their shape and their size is going to depend on their function in the machine. Are they aimed at the acceleration of the beam, at the deflection of the beam, or at the combination for deflection or combination, or to confine the particle bunches during the beam transport. So other factors that are at play are going to be the mode employed for acceleration, the nature of the particle that's accelerated, the specific parameter for the machine, such as the total energy, the type of science and conductivity for use. So each cavity is targeted for a specific use and certain specifications in the machine. And sometimes in a machine, you have several types and several shapes of cavities.
Okay, great. And you mentioned niobium as a superconducting material. Materials can be used for superconductor applications.
Well, there are thousands of superconductors actually out there, but to name a few, especially that are useful for SRF applications, we have compounds of niobium, such as niobium titanium nitride, niobium nitride, niobium 310. We have a more recent discovered superconductors at MgB2. And you have also other classes of material that have been discovered, more recently, such as the 2D conductors, that are, for example, iron selenide. And you also have, another class of material is called the metamaterials. It's basically the combination of several materials superconducting and insulating in very, very thin layer in order to modify the properties of the base material.
Okay, and it looks like the last question I have for you today was from our live chat. Is niobium better than copper?
That's an excellent question. For accelerators, niobium, because it's a superconductor, it allows us to operate a machine at very low temperature, but continuously, such as CEBAF, right? We have a continuous wave machine. That means that we need to have cavities that sustain the power continuously turning the machine off. In this case, niobium is better than just bare copper. But I will argue that niobium on copper, which is a mix of the two, can be equally as good.
Well, thank you, Anne-Marie. And now, last but certainly not least, we take you on a tour with Jonathan, our head of cryogenics, to explore the two largest cryogenic refrigerators on the planet.
Cryogenic refrigeration is key to many of the technologies that enable research at Jefferson Lab. The lab's 3 accelerators have components that must be cryogenically cooled to operate. These components include superconducting accelerator structures, magnets, targets, and accelerator component testing facilities. In all, Jefferson Lab has 5 major cryogenic refrigerators on site. 2 of these are the largest single 2 Kelvin refrigerators in the world. Lab's 2 central helium liquefiers together chill more than 30,000 gallons of warm helium gas to high pressures and then sending it through cold boxes. The cold boxes usher the helium through a sophisticated system of tiny turbine expanders each spinning thousands of times per second, followed by a set of complex heat exchangers. The system removes energy from the helium and reduces its pressure until it becomes a superfluid without resistance and conducts heat freely. The central helium liquefiers work together to cool particle accelerator components and the low-energy recirculator facility to their operating temperature of 2 Kelvin, or minus 456 degrees Fahrenheit, just a few degrees above absolute zero. Jefferson Lab's cryogenics personnel design, build, operate, and maintain the lab's cryogenic refrigeration facilities, and have provided their expertise to research facilities in the United States and around the world.
Hello, I'm Jonathan Creel. I'm head of the cryogenics department here at Thomas Jefferson National Accelerator Facility. Our group is about 50 people, including engineers, technicians, welders, and pipe fitters, and our mission is to design, build, and operate some of the largest helium refrigerators in the country. These refrigerators reduce temperatures down to negative 456 degrees Fahrenheit. In order to do that, we have to get ultra-pure helium, which has no contamination, because any contamination in the helium will be a solid at the temperatures that we operate at. So the first thing we do is take the ultra-pure helium into some that have horsepower ranges of 800 to 500 horsepower. They consume approximately 5 megawatts of electric power, or about the amount of it takes to power 5,000 homes. The compressors compress the gas up to very high pressures so that we use it in the refrigeration equipment. Behind me, you see the first refrigeration equipment where the helium is changed in temperature from room temperature, or about 70 degrees Fahrenheit, down to about liquid nitrogen temperature, which is around negative 320 degrees Fahrenheit. Once the helium is at minus 320 degrees Fahrenheit, we're going to move it to the 4.5 refrigerator, which we're going to go see now. This is the main 4.5 Kelvin refrigeration room. This is where the helium from the outside pre-cooler unit. It enters through the transfer line system you see above me on the wall. When it refrigeration unit cooled down to lower and lower temperatures using the equipment that we're going to go up on top and see now. Now we're on the refrigerator. This contains valves that control the flow of helium around the heat exchangers that are inside of this box below. They also control the flow of helium into turbo expanders like these here. These turbo expanders take high pressure helium and they spin a turbine wheel that expands the gas and lowers and its temperature. This is a cryogenic expansion turbine. It takes in the high pressure helium and forces the wheel to spin at speeds of up to 250,000 revolutions per minute. It does mechanical bearings. It uses a gas stream around the shaft to hold and allow it to spin at these incredible speeds. It basically gets transferred from this side of the turbine to this side. The gas on this side gets colder, and the gas on this side gets warmer, where it's cooled in this water jacket, which sends the energy out to our cooling towers. Next, we're going to go to the 2 Kelvin machine, the last part of the refrigeration process. Now we're on top of the 2 Kelvin refrigerator. Normal helium at 1 atmosphere is 4.5 Kelvin. To lower the pressure. This machine lowers the pressure from 1 atmosphere to 0.039 atmospheres, which is 2.08 Kelvin. This machine does this using these 5 cold compressors, which spins at speeds of up to 50,000 RPM, and they draw a vacuum on the helium that lowers its pressure. The 2.08 Kelvin helium is then used to cool components which are in the main accelerator. The next stop is going to be our control room, where we control these refrigerators. This is the cryogenic control room where we change the operations of our cryogenic plants. The engineers behind me are using computers and programmable logic controllers to change the operational modes of the plants and to direct where the cryogens are fed to the various loads on site. Thank you for your time. I appreciate it.
Wow, Jonathan, really cool stuff. I have several questions from you from our viewers as time. First one is, why do you use helium?
That's a great question. We use helium as a refrigerant because it's the only substance known to man that's not a solid at the temperatures we operate at. And so we can't use things like Freon or carbon dioxide or other things that you may have heard of that are used in some refrigeration system.
Awesome. And where does helium come from?
So helium, interestingly enough, comes out of the ground. When they're taking natural gas out of the ground and processing it for use as a fuel, a very small percentage of that natural gas is helium. And so they will set up helium reclamation units at natural gas facilities, and they'll slipstream that gas off and then take it out and put it into a liquid form where they deliver it to the facility that we buy from.
So where does the heat go when you cool things down?
That's a good question too. So basically, things here at the Accelerator that y'all have heard about, the series of steps that we do for refrigeration are basically to move heat from the we're trying to cool to things that we don't care about if they get warm. And so in our system, we move heat from the things we're trying to cool through the refrigerator all the way out to the cooling towers, where the big, huge cooling towers cool things down with water and big fans. And so we're moving that temperature or that heat through that environment and expelling it to the outside atmosphere.
How much electricity does it take to cool something down to 2 Kelvin then?
So that's a good question too. So again, we have 5 refrigerators on site. 2 of them are these very low machines, and each one of those 2 Kelvin machines draws about 5 megawatts of power on average. And if you think about it, that's about how much power it takes to operate 5,000 houses. And if another unit measure would be to say each watt of cooling that you need at 2 Kelvin costs you around 600 watts to 1,000 watts of utility power, depending on how you're doing the refrigeration cycle.
Can you tell me, are the extreme cold temperatures dangerous?
Yeah, so we have to be very careful in doing the work that we do. The temperatures, you're down at 320 below zero, 450 below zero. And so that if your skin gets exposed to that, it can cause instant frostbite and it can damage your skin tissues pretty quickly. And so we're very careful. We train people very carefully. We make sure people are very confident, and we make sure that we're wearing the appropriate safety gear whenever we go out to do anything. And we'll plan out actions very carefully so that we make sure we minimize our risk.
Okay, and why do things need to be cold?
Well, like you've heard from some of the other experts on here at in order to make the accelerator operate, we have to be able to niobium cavities and other metals down to superconducting temperatures. In order to get them down to superconducting temperatures, we have to use these large refrigeration systems down to 450 or 456 below zero. And so basically, we use these large refrigeration systems in order to help the accelerator be able to do its job and accelerate the electron.
Great, thank you, Jonathan. And one last question I have for you today. Do you have operators on shift all the time while the cryogenic system is online?
That's a good question too. So basically, our systems, so that they're, for the most part, computer controlled. And so we don't have operators that are sitting in our control rooms 24 hours a day, 7 days a week while the accelerator is running. The computers that we've programmed know what the operational envelope equipment are. And if the cryogenics equipment deviates from its normal operating conditions, it will set alarms that then get operators called in where they can diagnose and change the behavior of the machine or call in people to help repair things. Our equipment is programmed basically so that as the load of the accelerator changes, our refrigeration units will automatically follow that load so that we're always providing what's needed to cool the accelerator, but not more than that, so that we're not wasting electricity, we're not wasting liquid nitrogen and other power, valuable resources.
Well, thank you so much, Jonathan, and thank you to all our viewers for sticking with us through the live stream and the technical glitches that we experienced. After this broadcast, we will post a full version of the live event on our YouTube channel. Also, you can visit the event webpage at jlab.org/VFT2021 for additional resources for teachers that would like to use this for future lesson planning, as well as some great student activities. Now let's check back with our lab director for some thoughts. Stuart, back to you.
I hope you've enjoyed this field trip to Jefferson Lab. You've seen a truly unique scientific facility firsthand and got to hear directly from some of our scientists and engineers about Jefferson Lab and the exciting work that we do here. On behalf of our dedicated staff and the teams of scientists who make use of our world-leading facility, we're proud of the science that we accomplish here, and we're very happy that you've joined us to learn more about Virginia's National Lab. Thanks so much for your time, and thanks for visiting.